Hi, I'm Lynn and I am a chemistry teacher here at the Dublin Academy, and in today's class I'm going to go through two volumetric analysis questions, so question 1 from the Leaving Cert exam. The first one we're going to have a look at today is on the water crystallization titration, so we'll go through the theory of that titration and then we'll go through the all-important calculation, and then the second one we're going to go through today is the bleach titration. So for those of you in my class in the day school, we did have a look at the first one of these titrations in our class this week, but we didn't get to go through our calculation, and then I want to make sure we emphasise the bleach titration, so we'll have a look at that today as well. Okay, so we'll get started, and if you have the worksheet in front of you, the two questions are there, so if you can follow along with me with those questions and we'll have a look at them. So question 1 on the sheet, as I said, relates to the water crystallization titration. It's from 2006, so it's question 1 from the exam in that year. If you don't have a copy of the worksheet, you can look it up on examinations.ie, and we'll have a look at, as I said, the theory initially, and then we'll go through the calculation. So we're first of all told that we have an experiment that was carried out to determine the percentage order of crystallization and the degree of order of crystallization, which is our X value, in a sample of hydrated sodium carbonate crystals. An 8.20 gram sample of the crystals was weighed accurately on a clock glass and then made up to 500 centimetres cubed of a solution in a volumetric flask. A pipette was used to transfer 25 centimetre cubed portions of this solution to a conical flask. A previously standardised 0.11 molar hydrochloric acid solution was used to titrate each sample. A number of accurate titrations were carried out. The average volume of hydrochloric acid solution required in these titrations was 26.05 centimetres cubed. So we already have a lot of information there in that question that we need to collect. And as always, I would encourage you to make sure you are highlighting those all-important figures as you read through that paragraph. So, we've got a mass there that we need to make sure we highlight, because that's going to be important in our calculation. We have a volume for our solution, 500 centimetres cubed. We need to highlight that. Our 25 centimetre cubed portions of our sodium carbonate solution, the molarity of the hydrochloric acid, and then our average titration value. We need to make sure we've highlighted all of those figures before we go on to the next part of the question. So what we're trying to do here with this titration is we're trying to determine the level of hydration in our hydrated sodium carbonate. So if we just have a look at this formula here, this Na2CO3X H2O, what this is telling us is that for every sodium carbonate molecule, we have a certain number of water molecules associated. So that is a fixed ratio. Okay, so for every 1 sodium carbonate, we have X number of water molecules, and we're trying to figure out what that ratio is in our calculation in this experiment. The titration reaction itself is the reaction between sodium carbonate and hydrochloric acid. So this is a base and an acid where we produce a salt, carbon dioxide and water. Okay, so what we're trying to do here is we're trying to figure out how much sodium carbonate reacted, and then we can relate that to the mass of hydrated sodium carbonate that was used. So by relating those two figures together, we can determine that value of X. Okay, so that's going to be our first focus in our calculation. We're going to try and work out the concentration of the sodium carbonate. So let's have a look at the next part of the question. So in part A, we're asked to identify a primary standard reagent which could have been used to standardise the hydrochloric acid solution. Okay, so hydrochloric acid is not a primary standard. So before we carry out a titration such as this, we need to determine its concentration. We're told in the question that its concentration is 0.11 moles per litre. That has been determined by a previous titration. Okay, so the compound that we can use to do that is anhydrous sodium carbonate. Okay, so that's our answer there to part A of the question for 5 marks. Anhydrous. It is important to include this because if you just say sodium carbonate, do you mean the hydrated version or anhydrous, which of course means dry? Okay, so no water is associated with the sodium carbonate. So in part B of our question then, we're asked to name a suitable indicator for the titration and state the colour change observed in the conical flask at the end point. So our indicator is methyl orange, and our colour change is orange, or we can say yellow, to pink, or we often say red. You'll see when you look at the marking schemes for these questions, you will see that there are usually a number of accepted colours, but do just be careful that you have it in the right way around. So you're saying orange or yellow to pink is our colour change there. So you get 9 marks for that. So methyl orange, 3 marks for naming your indicator, and then for the correct colour change that we see at the end point. And then the final part of part B, explain why not more than 1 to 2 drops of indicator should be used. So the reason why we do not add more than 1 to 2 drops of the indicator in our titration is the fact that the indicators that we use in these titrations are acidic. And if by adding too much, we're going to affect our end point, because we will be lowering the pH of the solution in our conical flask before we've even started the titration. So we make sure that we don't add too much, because we'll affect the end point. So the indicator is acidic and will affect the end point. Okay? So as we can see there, that part of our question was worth 12 marks. So we've got 5 marks for part A and now 12 for part B. Now on to part C of the question. So as we can see, part C of the question is divided up into 2 parts. The first, we're asked to describe the correct procedure for rinsing the burette before filling it with the solution it is to deliver, and then why is it important to fill the part below the tap of the burette. Okay, so this is worth 12 marks, 6 marks for each part of part C. So if I just clear a little bit of space here. The first bit, we're asked about our washing procedures for the burette. So what do we need to do to prepare the burette for our titration? So the first thing we need to do with our burette is we need to wash it thoroughly with deionized water. And then we rinse it out with the solution it will contain, okay, which in this case is our hydrochloric acid. So we wash with hydrochloric acid. Okay, so we've got our 6 marks there. We have 3 for mention that we washed it with deionized water, and further 3 marks for mention that we wash it with the solution it is going to contain. And that's always the procedure for preparing the burette, regardless of what titration you're being asked about. In part 2 then, we're asked why we fill the portion of the burette, the part below the tap. So until you fill the part below the tap, we basically have air in the burette. So we need to make sure that we fill that part below the tap, because it has been calibrated for that volume to be included in the overall volume of the burette. So if we don't fill the part below the tap, our final answer, the final volume that we record, is not going to be an accurate one. So we need to make sure that we open the tap and fill that portion. So we can just say here in this part that if we don't fill the part below the tap, it will affect the result. Okay, because as I said, that the volume below the tap is included in the overall volume of the burette. So we need to make sure we include that. So that's a further 12 marks. So we've now got 29 out of our 50 marks in the question, and it all relates to the theory of our titration. We haven't had any calculations to do yet, and often, you know, students are so focused on the challenges of the calculation that they forget about the importance of knowing the theory of your titrations really, really well. That's as important, or often even more important, than the calculation. So it is very important that you know the theory well. So we're moving on now to part D and E, where we have our calculation. So we're going to have a look at this now for 21 of our 50 marks. So in part D, from the titration figures, calculate the concentration of sodium carbonate in the solution in moles per litre and in grams per litre. And now this is where all of those figures that we highlighted in the question are going to be important, and we're going to be using these. So if I just move over here, we'll just have a look. What we're going to do now is we're going to collect that information from the question. Okay, so I've just drawn a simple table here that we can fill, and this is going to help to guide us through our calculation. So we need to look at the molarity, first of all, of our sodium carbonate and of our HCl. So the molarity, which don't forget, molarity means moles per litre, so the concentration of our solution in moles per litre. We don't know that for our sodium carbonate. That's what we're trying to determine here. That's what we're trying to figure out. So I'm just going to put a question mark there because that's our unknown. The concentration of our hydrochloric acid, we're told, is 0.11 moles per litre. Okay. The volume of sodium carbonate used is 25, and this, remember, this is all information in the question. And then the volume of our hydrochloric acid, which was in our burette during our titration, that's our average titration figure. And if we look at the question, we see that's 26.05 centimetres cubed. Okay? And then finally, the ratio. So this is the ratio of one compound to another. In our titration, we're reacting two things together, and we need to know their ratio in terms of number of moles. And we get that from our balanced equation. So you're always given the balanced equation in the question. And what you need to have a look at here in the balanced equation is what is the ratio of sodium carbonate to hydrochloric acid. So if we have a look at this, for every one molecule of sodium carbonate, we have 2 molecules of hydrochloric acid. So we can see that they are in a 1:2 ratio. Okay, so that's what I'm going to fill in here, 1:2. Okay, so we're ready to start. We are trying to determine the molarity, our moles per litre concentration of sodium carbonate. Okay, now to do that, we have to first of all focus on the information we have about the hydrochloric acid. So we're told in the question that our hydrochloric acid solution is 0.11 moles per litre. So the first step, and this is common to all titration calculations, the first step is to figure out the number of moles in the volume used in the question. So 0.11 is the number of moles in a litre. Okay? So the first thing I'm going to do is I'm going to divide by 1,000. So by dividing by 1,000, I will be able to figure out the number of moles in 1 centimetre cubed. And then I'll multiply by 26.05. Okay? So I've divided by 1,000 to work out the number of moles in 1 centimetre cubed, and now I'm multiplying by 26.05. Okay? Now I always say this in class, but I would encourage you to follow along with me in your calculator. Make sure you're doing the calculation yourself as I work through it here on the board. Okay? So if we do that calculation, we see that we have 0.002866 moles in 26.05. Okay? 26.05 centimetres cubed, which is our average titration value, contains that number of moles. Okay? Now again, your calculator might give you that figure in scientific notation, which is absolutely fine. Don't feel under pressure to convert from one to the other. They're both accepted, okay? So if you're happier with scientific notation or with the notation at the bottom, it's completely up to you, okay? Now, what we want to do is we want to relate this number of moles to the number of moles of sodium carbonate that reacted during this titration. And this is where the ratio from the balanced equation is significant, because if we have 0.002866 moles reacting, okay, of hydrochloric acid, and they're in a 2:1 ratio, to work out the number of moles of sodium carbonate involved in this reaction, we simply divide by 2, okay? And that will then tell me the number of moles of sodium carbonate, involved in this particular reaction, okay, which we see as 0.001433 moles. And that's in 25 centimetres cubed, okay, in the volume of our solution, okay? So that volume of solution contains this number of moles, okay, and we've been able to determine that from our calculation. So what we need to do now is we need to scale this up. we now know the number of moles in 25 centimetres cubed, but we need to determine the number of moles in a litre. So we're going to take that figure, that's 0.001433, we're going to divide it by 25, and then we're going to multiply by 1,000. And let me just explain why we're doing those two steps. We're dividing by 25 so that we know the number of moles in 1 centimetre cubed of our solution, and then we're multiplying by 1,000 so that we know the number of moles in a litre. Okay? So our answer to that is 0.0573 moles per litre. Maybe off the edge of the board there. So 0.0573 moles per litre. Okay, so that's our first answer required by the question. So I'm just going to highlight it, and I'm constantly saying this, but again, when you work your way through these calculations, highlight your final answer, because when the examiner comes to your calculation, and sometimes it gets a little bit chaotic, and the numbers might be a little bit scattered across the page. Direct them to your final answer so that they can give you all the marks available. Okay, so that's the answer there to D part 1. Okay, so now we need to convert this from moles per litre into grams per litre. So I'm just going to rewrite that figure here just so that it's a little bit clearer. Okay, now 0.0573 moles per litre, we want to convert that into grams per litre. So to go from moles to mass, of course, we multiply by our molecular mass. So the molecular mass of our sodium carbonate, Na2CO3, is 106 grams per mole. Okay, 106 grams per mole, which of course we would just simply work out by adding up the masses of the atoms in that molecule. 23 times 2 plus 12 plus 3 16s for the oxygen. So we're going to now multiply 0.0573 moles per litre by 106 to get our concentration in grams per litre. Okay, and if we do that, we get 6.074 grams per litre. Okay, so that's our second answer there for part D. So that's D part 2. So we're working our way through our calculation here in D part 2. So we now have 9 marks. We still have a further 12 to get, okay? And this part of our calculation is almost identical to the first part of any calculation for any of the 9 titrations on the course, okay? So being able to work through your calculation in this way is very important, because as I said, it's common to all of the titrations. The next part is where things get a little bit different for this specific titration, okay? So I'm just going to move over here to the middle just so that I have a little bit more space to have a look at the final part of this calculation. So, in part E of the question, we're asked to calculate the percentage water of crystallization present in the crystals and the value of X, which is our degree of hydration. Okay, so we have our grams per litre value. So I'm just going to rewrite that over here. So 6.074 grams per litre. Okay, so that's the mass of sodium carbonate. Not hydrated sodium carbonate, that's the mass of anhydrous sodium carbonate that was involved in this reaction. But if we read back to the start of the question, we see that we didn't prepare a litre of solution. 500 centimetres cubed was prepared. So what we need to do here is divide this number by 2 to find out how much sodium carbonate was actually in the solution prepared in this experiment. So we divide 6.074 by 2, and we get 3.0374 grams in 500 centimetres cubed. Okay? So that's the mass of sodium carbonate in our solution. Now, we are told in the question that we have, this is our hydrated sodium carbonate, okay? And we are told at the start, but at the very beginning of our question, that we have 8.20 grams of this hydrated sodium carbonate. We have now worked out that there's actually 3.3 3.0374 grams of sodium carbonate. Okay? So that means that the mass of the water in our hydrated sodium carbonate must be 8.20 minus 3.0374. It has to be the difference between those two figures. Because if this is the mass of our hydrated sodium carbonate, the sodium carbonate plus the water, and this is the mass of our sodium carbonate on its own, then we must be able to simply work out the mass of the water by subtracting one from the other. So if we do that, 8.20 minus 3.0374, we get 5.163 grams. Okay, 5.163 grams. So what we need to do now is we need to work out the ratio of sodium carbonate to water in this compound, in this hydrated crystalline substance. And to do that, we need to divide by the molecular mass in each case. We need to get back to number of moles, because remember, we're looking here at the ratio of sodium carbonate molecules to water molecules. So we need to bring this back to number of moles, and we do that by dividing by the molecular mass, okay? So we're going to divide each of these by their molecular masses. We've already worked out that the molecular mass of sodium carbonate is 106. Oops, sorry. 106. And then, of course, water, we're going to divide that by its molecular mass, which is 16 plus 1 plus 1, which of course is 18. Now, so for the sodium carbonate then, we get 0.0287, and then for the water we get 0.287, okay? So now we can see the ratio of one to the other, but we don't have this in a simple whole number ratio yet, okay? So to work out the simple whole number ratio, we just divide both of these figures by the smallest of the two numbers, okay? And if we do that, we see that they're in a 1 to 10 ratio, okay? They're in a 1 to 10 ratio. So that means that in our formula, Na2CO3XH2O, the X is 10, okay? So X equals 10. So for every 1 sodium carbonate, we have 10 water molecules associated to it, okay? We're very nearly there. We've one final thing to do here, and that's to work out the percentage of water of crystallization. This is the final thing we need to do in part E of this question. So to work out the percentage of water in this molecule, we simply just divide the mass of the water, which is 5.163, the mass of our water, by the total mass of our hydrated crystals, which is 8.20, and we multiply that by 100 to work out our percentage, and we get 62.9%. 62.9% as our final answer, okay? So I'm going to highlight that, and I'm also going to highlight this because this is our value for X. So these are the two answers for part E of this question from 2006. Okay, so we've gone through a full 50-mark question there, which is a very typical question for that water of crystallization titration. Okay, thank you.